Hello, my name is Roman Jerger, and today we will be discussing Sherwood, Reynolds, and Schmidt numbers as dimensionless groups. We will be to fit to data using a correlation of the form Sherwood is equal to A by generating 100 pseudo-experimental points with a given 10% correlation normally distributed experimental error. So to begin the problem, we must start with what we know. This problem is from the textbook, so I'll be reading off the description of the problem here below. In this figure, you can see that we start with a volatile, pure liquid that is allowed to flow down the inside surface of a circular tube while gas is blown upward or downward through the central core. Measurement of the rate of evaporation of the liquid into the gas stream over the known surface permits the calculation of the mass transfer coefficient for the gas phase. Gilligand and Sherwood studied the evaporation, and their correlation is the Sherwood is equal to 0.023 Reynolds number to the 0.83 power multiplied by the Schmidt's number to the 0.44 power. Here the Reynolds numbers is very from the lower bounds of 2,000 to 35,000, and the Schmidt's number is from 0.6 to 25, 25, where the characteristic length is the Sherwood number and the Reynolds is the diameter of the tube, and the physical properties of the gas are evaluated at the bulk conditions of the following gas stream in this figure. So to start with this problem, we need to list what the important variables are. Again, I pulled some of these this table from the book just for means of time, that I wouldn't have to write down all the words and everything. But here in the textbook, they use their dimensions and variables. Here you can see they have the tube diameter, the fluid density, the fluid viscosity, the fluid velocity, the mass diffusivity, and the mass transfer coefficient. Now in the textbook, they determine the dimensions and lengths of time and mass and length. Now I'll be converting this because it'll be easier to do some of the equations that we'll be doing later within this problem. But for now, length is equal to meters, mass is equal to kilograms, and time, or T, or time, is equal to seconds. Now we know that the diameter is then equal to meters, the fluid density is kilograms per meter squared, the fluid viscosity is kilograms per meter second, and the velocity is meters per second. The mass diffusivity is meters squared per second, and the mass transfer coefficient is meters per second. So with this given information, and we know what the dimensions are, we will be utilizing the Buckingham pi method, which is I is equal to n minus r, where n is equal to the number of variables within the problem, and r is the rank of the matrix. Now we'll need to be utilizing this I to be our dimensional groups, and how many groups or how many equations we'll be needing to determine the dimensional groups. Now we'll be utilizing a dimensional matrix, which is a matrix formed by tabulating the exponents of a fundamental dimensions. Here we'll be using it as meters, kilograms, and seconds, which appear in all of these dimensions. The rank of the matrix is the number of rows in the largest non-zero determinant, which can be formed by it. I will show you the rank of the matrix in Python later, and where now we will start to tabulate what the exponents are. Now to begin this problem, we need to determine how many times how many times within the variable that a certain dimension occurs. So I'll begin by writing down the terms like this, where the symbols are at the top, where you have the tube diameter, the fluid density, the fluid viscosity, the fluid velocity, the mass diffusivity, and and the mass transfer coefficient. Now we'll be determining these and ranking them by the exponential value of each of the core dimensions, which is meters, kilograms, and seconds. Now the diameter doesn't involve kilograms or second within its dimensional properties. So we'll be putting a 0 right here for them. Now we can see that diameter has meters, but the meters is not raised to a certain power. So therefore, or you could say it is raised to a power, it's raised to the first power. Now we'll utilize the rest of those of that knowledge to our advantage, where we know that the density is mass divided by meters cubed. So we know that this will be -3 because mass is raised to the third power in the denominator, and we know that the mass is in the numerator raised to the 0th power. Now we'll be continuing utilizing this method for all of these variables, and we will be putting all of these variables into a design matrix, and then we will be determining what the rank is. Then, with that number, the rank, we can then determine how many Buckingham pi equations that we will need to figure out what our dimensional or dimensionless numbers are. So I'll continue writing down these properties for our matrix. We have the viscosity, which is kilograms, and seconds and meters. We have velocity, which is length, meters, and we have time, so we don't have kilograms. Time is in the denominator. Time is, in fact, a denominator, and the rest of them down here. Sorry. Length of time. And we do not have mass. Two, and 1. Now we'll be grabbing all these terms and putting it into a design matrix. Now the matrix will look something like this. It's P, -1, 1, 2, and 1, 0, 1, 1, 0, 0, 0, and 0, 0, -1, -1, -1, -1. Now we will be determining the rank of this design matrix here in Colab. So let me just pull that up real quick, and I'll get right on that. So now with all the information that we determined from the design matrix, we will be using Python to determine the rank of the dimensional matrix, or the design matrix. So to begin, we're going to import numpy as np, and then we will be utilizing numpy's linear algebra function, and within that function we are going to be using the built-in matrix rank. Then we will be putting the design matrix that we determined from the problem into here, and I had, let me check my paper, we had 1, comma, -3, comma, -1. 0, 1, 1, 0, 0, 0. We had 0, 0, -1, -1, -1, -1. And then we're going to Shift Enter. And we have determined that the rank of our matrix is 3. Now I will be going back to my notes here, and then we'll be utilizing the Buckingham Pi method. So we know that the number of variables that we utilize within this problem is 6, and using Buckingham's Pi method, you do the number of variables minus the rank. So then we know that we need to utilize 3 of the Buckingham Pi method equations to figure out our dimensionless groups. From there, we will be utilizing the core functions for the Buckingham Pi method in the equations to determine equations to use that as a system of equations. So let me roll over there real quick, and then I'll reiterate just to make things a little bit more clear. So now that we know what the rank is using Python, we will utilize the Buckingham Pi method to determine our dimensional numbers. So to begin with that, we'll write out some equations, pi1, pi2, pi3. Now we need to determine some dimensions or variables that occur within the within this function frequently. So I chose the mass diffusivity, and I chose rho, the density, and chose the diameter. Now these will be all kept the same, and then we'll use the system of equations to figure out our desired variable. Now our desired variable is the mass transfer coefficient, the velocity, and the viscosity, mu. Now, to start this problem, we actually need to raise our core 3 functions to a specific power, or what we will determine as unknowns. So I will name it A, B, C, D, E, F, G, and H, and I. Then we will be to break down these variables into their dimensions, and then using that as a matrix to determine that to be a system of equations. Now let me show you how we would do that. So here we have pi1, which will be equal to the core values, meters, kilograms, seconds, which is equal to the mass transfer coefficient, not the mass transfer coefficient, the mass diffusivity, which is meters squared per second. And then we'll multiply that by the density, which is kilograms per meters cubed, and then multiplied by the diameter, which is meters. And then at the end, we have the mass transfer coefficient, which is meters per second. And then we need to plug in our unknown exponents. Now, we will be utilizing what we did previously with the design the design matrix, and we'll be plugging these in to be sort of like a system of equations. So here we have meters, kilograms, seconds, and as you can see, we have meters occurring 2 times, which we'll have 2a, and then we have meters occurring down here, so minus 3, B plus C. And then because the mass transfer coefficient isn't raised to an exponential value, but it is occurring within this equation, it will be 1. Pardon me, let's just pause here. I'm having some technical difficulties. And I'll be right back. I'm back. My tablet had crashed. So where were we? These equations are all equal to 0, and then I am determining what the exponential power of each variable is based off their functional or their core function group, which is meters, kilograms, seconds. So then we determine that kilograms occurs in the numerator here, only to the first power, so that's just B, which does not occur anywhere else. So B, we know, is equal to 0. Now we have seconds. We see that it occurs in the denominator. So it's negative A, and then it occurs, oops, sorry, that's not a negative. Or that's not a positive, that is a negative 1, because it occurs in the denominator for the mass transfer coefficient. So then we know, based off this information, that A is equal to negative 1, and we plug all of that into the beginning equation. So we have negative 2 minus 0 plus 1, and so we have 0 equaling, or C equaling 1. Now we put that into our equation here, and we will plug these into A, B, and C from pi 1. So we then get the diffusivity coefficient in the denominator, and then we get the diameter in the numerator and multiplied by the mass transfer coefficient. Now, if we look back, we can quickly determine that this actually is the Sherwood number. Now, we will continue doing this with pi 2 and pi 3. And I think we will see that this will also become numbers that we recognize. So we got pi 2. And if we do quickly realize, we'll see that pi 2 actually ends up having a similar type of system of equations, just because it does use the same couple of variables, and velocity is actually the same functional groups. So I will write that out to be similar to that. And here's cubed. Let's do that. Meters. And we know that that is meters per second. Now, we're not going to reuse A, B, and C. We determined it would be D, E, F. And we know quickly that it'll actually be the same. So we have 2D minus 3E plus F plus 1 is equal to 0. And let's see, it will be E this time is equal to 0. And then we have negative seconds, not 2. Minus D minus 1 is equal to 0. And then we can see again that pardon me, that it is the same, but it is multiplied by the velocity. So we get that pi2 is equal to the diameter multiplied by the velocity over the mass diffusivity. Now we will actually determine that we actually know that's the Planck number. And then we will determine pi3. I'm going to try and open up a new window. It's getting a little messy. Pi3 is equal to meters per second, or meters squared per second, kilograms per meters cubed, and meters, and then we multiply by that by the viscosity, which is kilograms per meters per second. Now this will end up being a little bit different. As you can see, it's multiplied by a different core factor. Here's meters, kilograms, seconds. Got 2g minus 3h plus I minus 1 is equal to 0. With kilograms, got h plus 1 is equal to 0. And then we have negative g minus 1. So then we get g to be equal to negative 1, h is equal to negative 1. And that makes it negative 2 plus positive 3 is 1, which makes I equal to 0. Sloppy I. Now, if we can remember correctly, we have pi3 is equal to where g is negative 1. So we have the mass diffusivity in the denominator. We have, rho, which is h in the denominator, not q, rho. And then we do not have meters, and then we have the velocity. Now we know that to actually be the Schmidt's number. Now that we have correctly determined the dimensionless numbers, we will be utilizing that to in 100-point pseudo-experimental data, 100 pseudo-point data with a 10% error, and I will pull that up on Google Colab and we'll start coding. Actually, before we start coding, we're going to, because we know that we will eventually have to use linear regression on the Sherwood equation, we're going to do that linear regression right now, just so that we have all the writing stuff at the beginning of the video and the coding at the end. So we know that when we start with the Sherwood equation, we'll start something like this, which is similar to what you can think of as y equals mx plus b. But this will be the linear regression of the Reynolds and Schmidt number to the Sherwood number. So for the purpose of this, we will take the natural log of the Sherwood number on both sides of the equation. Plus CLNSC. Now, to start doing this part, we will actually, again, utilize a design matrix. Here we will begin in the coding. We'll use the same amount of Sherwood numbers that we expressed, but for instance, I know in the coding we're probably going to have 100 value points, but here for the sake of notes, we're just going to use 4, and then we'll use the Reynolds number, all of those values, and this again is just conceptual, so we don't actually need values at this point. And then we need some parameter, which I'll call P, which is equal to the natural log of the Sherwood number. So as we've created our design matrix, we know that we actually need to change the name of this first function, just for sake of ease. So this first function we'll actually call dm for our design matrix. We have our unknown parameter p. Excuse me. And then we have our matrix of the ln, or the Sherwood number to the natural log. Now we know that when we need to do the linear regression of the design matrix, we need to take the transpose of the design matrix, which is basically just flipping the rows and the columns on their side. So if you had a 2x4, now you have a 4x2. So we take the transpose, which you need to do on both sides of the equation. So we take the transpose of the design matrix, and then we multiply the design matrix by the inverse. Now I'm going to combine the inverse and the transpose into one form, just for a little bit of cleanliness. We do that on both sides of the equation. And we know that if you multiply a number by its inverse, that number ends up canceling out. So next we simplify, and you see that we actually end up getting the parameter P is equal to the design matrix multiplied by its transpose by its inverse, and then by the transpose of the, sorry, I forgot that transpose up there, is equal to the Sherwood number. That's a little bit messy. Now that we have this linear regression function, we will go into Google Colab and we'll plot this out so that we can find the linear regression, and we'll use the minimize function, something to look forward to, and we'll start coding for real this time. So here we are, we're going to start coding. Here we will begin to get artificially make our 100 pseudo points with a 10% error correlation, normally distributed, and then we'll also utilize our linear regression formula that we had previously determined on our notes. And to begin coding, we are actually going to start bringing in some things. So we'll import numpy as np, Python's numerical function. We will also import some graphic stuff, or some graph stuff. So we'll import plotly.io as PIO for sake of naming, easier to name within the coding. Then we're going to import plotly graphs. Not graphs. We're going to import plotly graphs. Plotly dot graphs, graph objects as PGO. How about that? Or let's just name it GO. And then we will, no, not global. Don't want to do that. And then we will stop. Let's call it PGO because it doesn't like that. And then we're going to grab from SciPy SciPy.optimize, and we'll use the minimize function. SciPy import minimize. This will be for the linear regression. Let's spell minimize right. And then we will also, for our plot, we will make the background black. So we need to import plotly. No, we need to PGO dot templates and default equals dark, just so we have a background, dark background. Oh, not plotly underscore dark. I believe that's correct. Oh, not from. It is oh, sorry, not that. It's not PGO, it's PIO. All right. So to begin this problem, we had initially, sorry, I had some hiccups. We need to utilize the equation that we used from the textbook. I believe that it is the Sherwood number that we determined. 0.023. Let me just find that real quick. 0.23 times the Reynolds number to the 0.03 power multiplied by the Schmidt's number to the 0.44 power. And this is the Sherwood-Gilligand's equation. It's not pound, not 8%. Sherwood equation that they determined from their evaporation equation that we have previously found out. So this is the Sherwood-Gilligand's number. So next we need to actually determine or find 100 points for the Reynolds and Schmidt's number. This is something that we would find in the in the laboratory, but since we don't have access to a laboratory, we are going to make up these numbers with a experimental error, and we will do this both for the Schmidt's number and the Reynolds number. Now, to do this, we will import or use numpy random to generate 100 evenly spaced, which is what the uniform function is. Uniform. We will generate 100 points randomly that are equally spaced apart from one another. Now, we will utilize the ranges of these the minimum range and the maximum range, which again we were given at the beginning of this video from the textbook, which is 2,000 and 35,000. The third, and then we want 100 points. And then we want to do this the same for the Schmidt's number, but again, we were given different bounds. So we have randomly generated 100 points within uniform data sets. And I spelled form wrong, so I'm going to use syntax error. And then this will be 0.2, I believe. No, 0.6 and 2.5 within 100 points. Let's check that out. RE is not defined. This is not defined, so actually I need to put this underneath here so that it can define it as a function. Go messy, messy, messy. And then I want this right there just to let it know that it is cool. Print Reynolds number. So as you can see, this is it. 100 points randomly generated within the bounds of the Reynolds number, and this is the bounds within the Schmidt's number. So next, we want to start doing our Sherwood number and how we will correlate that. So let's start. Start by generating points for the Sherwood number. The Sherwood is equal to, Sherwood, we are going to generate 100 points at random intervals, but these will not be at a uniform length. They will be at a normal length. This will create those 100 data points, and then we will locate it utilizing location, and then we will use the scale function, and we will set that to the error. So this equation is the 10% error within our equation. I don't need a size. but I do need to multiply that by the Sherwood number. And this is our experimental error. We're going to look at that. As you can see, uniform 100 points of the Sherwood number. And this is basically what we'll be doing, doing the linear regression. But for the sake of linear regression, I will demonstrate how to do that here. So to go on to the next part, we're going to do the linear regression of the Sherwood's number, which we had previously done. If you can remember, that was the design matrix where we had the natural log of the Sherwood number is equal to the natural log of A plus the B times the natural log of the Reynolds number plus C times the natural log of the Schmidt's number. So here we are going to actually calculate this within Python, which I said we would be doing. And if you can remember, we actually ended up doing this as we started off the problem by creating a column, np column underscore stack, which basically grabs our, we changed the Reynolds number matrices that we previously found within this line right here, and then we're going to put that all into one row, one column, and then we'll put the Schmidt number into a column, and then we will actually have our first problem, our first left-hand side. We said in the writing we did 4 ones, and for this we're going to use the same number of the Reynolds numbers, which was 100 points. So np dot one ones like creates those values of 100 ones within that that matrix, and then we're going to take the natural log of the Reynolds number and the natural log of the Schmidt's number. And then if you remember correctly, we actually have already determined the linear regression equation, where I had determined my my parameter to be p, and then we multiplied our equation by the design transpose matrix of the inverse of the transpose matrix, and then we multiplied that by the natural log of the Sherwood's number. So I'm going to be typing that out. We have NP algebra of the inverse, and then we have our matrix dm, and then dot t, which is the transpose, multiplied by our design matrix, and then we're going to multiply that all, which I've already said, by the transpose multiplied by the natural log of the Sherwood number. Oop, not SH. Type error. What is my type error? Oh, I don't have this as a matrix. Not T. There we go. Okay. So if we want to see that, we want to print our variable, and then and as you can see here, these are actually very close to the values, which is equal to close to what these numbers are. And we knew that already. So we've done the linear regression on paper. Now we're going to utilize the sum squared function within Python. Now this is the equation to figure out what the A, B, and C values are using the sum squared method instead of using linear regression. Here we will be utilizing the natural log of the Sherwood number minus the first value of the sum squared method plus the second value of the sum squared method multiplied by the Reynolds number, or the natural log of the Reynolds number. And then that plus the third value of the sum squared function multiplied by the Schmidt number. And then we are going to square all of that up. And there we go. Now we want to use the minimize function to be able to see this sum squared deviation. At the point of the Reynolds number. And 0.35. And that's not, those are not parentheses, they are brackets. And hope if I spell minimize right. Now, as you can see here, we have the values within this array right here to be the A, B, and C value within the nonlinear regression. So now we want to start plotting out our data points, and then we will create a mesh grid so you can visualize those points within the three-dimensional space. So let's begin to start graphing. So I had forgotten to import make subplots, so I was having little issues. So now I can create a subplot. And then we are going to make our 3D scatter plot. First, we'll use the add trace function and create the scatter function. Now we're going to define our functions. So the x axis will be the Reynolds, y will be the Schmidts, and z is the Sherwood. Then we want to figure out what our mode is. and we want our mode to be markers. Then we want to figure out our size, and I think probably about a marker size 4 ought to be good. And then we want to give ourselves a marker color. I think blue should be good. Name error. Markers. Marker. Markers. Blue is not defined. Well, let's make it, I believe I looked it up. 0.840 is blue. Oh, did not like that. Oh, like that. No, doesn't like that. Let's just give it its gradient. Nope, still doesn't like that. Oh, am I missing extra parentheses? There we go. So there's our three-dimensional plot, then space. Now we want to visualize this in three-dimensional space, and we will create a mesh grid. So we will first start by doing the Schmidt grid, and here we will create a set of values for the Schmidt number, and the values of the Schmidt number and the Reynolds number will one will stay constant and the other will vary, and vice versa. So then we'll get those nice grid lines going this way and then this way. So first we need to create our mesh grid. And make the line space equally distant. And these are the values of the Reynolds and Schmidt numbers. Line space and 2e3. This is just the upper and lower bounds of the Reynolds Schmidt numbers, and 20. And then we want to create the Sherwood grid, and that will be NP XP to the dm of the first value, and then multiply that by the Reynolds grid to the power of the it's not dm, it's p. Those values within that function. Grid to the third value. So now we are going to create our conditional statements for the individual lines that are crossing across the grid. So for this part, we want to have the variables be, let's say, A, B, C, because why not? And then we're going to zip them up. And this will grab both sides of one of the matrices and zip them together like a zipper. The zip function is within Python, and then we will grab those values of the Schmidt, the Reynolds, and the Sherwood, and we will zip them together. Then we want to create those lines. Add for trace. And then we want to put those lines. Go scatter plot D. Then we want our x values to be A, x, y equals B, and z equals C. And then we want the mode to be lines. And then we want the line color to be, let's make it gray. And then we want to do that right. And then for the next one, we want to, the next part, we just want to copy and paste this. And then we just want to flip the Reynolds and Schmidt number. We copy that, paste it, and bring that back. We want to switch these Reynolds and the Schmidts, and then switch these values. So we have this all situated. We're going to run this code. Appears that it doesn't want to show itself, so we'll force it. And we have our grid. So now we're just going to do a little bit of cleaning up. And we're going to get rid of that legend. And we're going to get rid of that title height and all that fun stuff. So we're going to update the figure. And we'll do figure.update layout, and we'll fix the width, make it 800, make the height 800 scene, dictionary, and we will change the access names. X-axis is the Reynolds, Y-axis is the Schmidts, and the Z-axis is the Sherwood. And we want to close that, and then we don't want the legends to show, so we'll do show legends equals false, or legend false. Don't want the F in lowercase. So we should be set here. Close that. Close that. And there we have it. So that video, this concludes our video. Hopefully it's informative, and hope you all have a great rest of your day. Thank you.